users will be able to. Expand and find the value of integers being taken to an integer power. And underneath power, I'm going to put in parentheses, or next to it, I'm going to write exponent. Because those words are fairly interchangeable. In other words, we can use those words most of the time and have them mean the same thing. All right, let's make sure that we've got a couple definitions in our head that come out of this aim in itself. Let's think about the word integer. What is an integer? Love the risk takers. We need more people involved here because we all know this definition. Kali, what's an integer?
A whole number.
A whole number. Kind of. A whole number would only suggest the numbers 1, 2, 3, 4, 5, 6, 7. Integers also include negatives and 0. Okay, so when we're talking about whole numbers, we're thinking about anything that is like a whole number or it's negative. So negative 1, negative 2, negative 3, negative 4, 0, 1, 2, 3, 4, and so on. When we're talking about a power, we're talking about an exponent. And this kind of leads us to this part that should be mostly review. So we're going to start with this part that's mostly review. Looking at this, we have 5 to the third power. This 3 would be called an... Jaquan? It would not be a variable. Remember, a variable is a letter that stands for number. Good idea, though. Somebody else. Jacob. Exponent. All right, so we have the 3 is the exponent and the 5, and this is a particular vocabulary term that we use mostly with exponents. So there was actually only one person in the previous class who remembered it. Let's see if there's anybody in here who remembers it better. What is this 5 in terms of exponents? Sammy, what do you think?
5 is the number that will be multiplied by itself.
So he's saying that he actually knows what the definition of this word is, but he actually doesn't quite know the word. He's saying, I know the 5 is the number that's being repeatedly multiplied. Does anybody know the vocabulary term for that? All right. The vocabulary term, and this is, we definitely need to write it down, is a base. So a base is the number that is being repeatedly multiplied with an exponent. So let's go ahead and write our definitions for base and exponent. Base is the number being repeatedly multiplied. And what does the exponent tell us? Dahlia? Yeah, how many times it's being multiplied? All right. So when we look at 3 to the 4th power, we can write this out in what we call expanded form. That means we're simply going to take the 3 to the 4th power, and we're going to write out what multiplication that represents. So the base tells me what is being repeatedly multiplied. In this case, it's 3. And the exponent tells me how many times. So it's going to be 3 times 3 times 3 times 3. And I have 4 3s because the exponent tells me to repeatedly multiply 3 times. And if I want to find the actual value, there's a few different ways of going about doing this. In my head, I kind of think about it as 3 times 3 is 9, times 3 is 27, times 3 more is 81. Is there anybody else who thinks through it in a slightly different process? Mina? Sammy?
I do, if it's an even number that's like, since it's 4 and it's even, I do 3 times 3, which is 9, and then the other 3 times 3 is 9, then I multiply 9.
Yeah, so Sammy says if it's an even number, I know they'll all pair up, and so he multiplies in pairs. He says this 3 times 3 is 9, and this 3 times 3 is 9, so 9 times 9 is 81. It gives you the same result. That uses the associative property, and it's totally fine. All right? So when we look over here at this next one, we have negative 5 to the third power. Notice the negative 5 is in parentheses. All right? This is to make sure that we understand that it's a negative number being repeatedly multiplied. Not that we want the negative of whatever the answer is. So that's why it's in parentheses like that. So when we want to expand this one out, our base is negative 5. And our exponent, 3, tells us that we're going to be repeatedly multiplying negative 5 3 times. So negative 5 times negative 5 times negative 5. This form of how we can write out a exponent is what we call its expanded form. So if we're ever asked to write an exponent in expanded form, all it's asking us to do is take the exponent and write it out with its repeated multiplication. Let's go ahead and make sure that we find the value for this. Negative 5 times negative 5 times negative 5. So negative 5 times negative 5 is 25 times negative 5 is negative 125. That's where we have to be careful of thinking about our good dates and our bad dates, which is why it's really nice to kind of group them and go, okay, well, this is 25 times a negative 25, times a negative 5, and that gives me a bad date, a 25 times a negative. A positive times a negative gives me the negative 125. You have to be super careful about those details. One thing that you should remember as an example, we're talking about a number to the first power, so something like 5 to the first power, or 21 to the first power. Any number to the first power is what? Itself. Is itself. Now you'll notice down here that I've written in parentheses that this is the identity property of exponents. Why would we call this the identity property of exponents? Think back to when we learned about identity property and what identity property means. Why would we call this the identity property for exponents? Take 10 seconds, turn to talk with your partner.
I think because it's time itself.
Yeah, because we have a operation that's being done and the value we get is itself. Just like 5 plus 0 is 5, or 5 times 1 is 5. An identity property is an operation that can be done without changing the value. So here we have something taken to the first power, doesn't change its value. All right? This is where we have to confront what we would believe and what our intuition would say and determine whether that's correct or not. Any number to the 0 power is
0, imaginary.
And this is where a lot of us kind of have our intuitions. And some of us think it's 0. Some of us would think it's 1. All right? We're going to leave that blank for just a minute. And we're going to watch a quick video which is going to do 2 things for us. Lola, what would be the next line in the pattern? Yeah, so she recognizes the pattern is that the 440 stays the same. The base is staying the same, but the pattern is that we're reducing the exponent by 1 each time we go to the octave. So when we look at that, what that means is that this 1 is equal to, it's the same thing as the 2 to the 0 power. So this is where our reminder comes in, where we talked about 2 to the 0 power is equal to 1. Now let's go back and fill in that blank over here. Any number to the 0 power is going to be 1. Anything to the 0 power is 1. All right? Let's continue that pattern. Let's come back over here. Let's think about what the next line in the pattern would be. Ignoring anything we see on the left-hand side, what would be the next line in the pattern? Turn and tell your partner what you think the next line in the pattern would be. Jesus, what do you think the next line would be? Read me the whole line. $440. Says times 1/2. Now that tells me that you're looking over at the left-hand side. All right? And that's an idea, but I want you to be looking only at this pattern. Sammy, what do you think the next line would be?
I think that the next line would be 440 by 2 to the negative first power.
Yeah, 2 to the negative 1, because we see it would continue the pattern. If you don't have that, make sure that you have yours fixed. We see that pattern is that the exponent is going down by 1. So if we're counting down by 1s, once we get to 0, we have to go into negative. So we get to negative 1. So as we continue to move down the line, what would the next line be? Jaquan? Yes.
The next line will be 440 times 2 to the negative second power.
440 to the, or 2 times 2 to the negative third power. And the last line down here is 440 times 2 to the negative fourth power. Now, if we go back and we remember, up here on these top parts, that meant that these parts were equal. They have to be equal. That means that 1/2 has to be equal to 2 to the negative 1. So 2 to the negative 1 has to be equal to 1/2. That means 2 to the negative 2 has to be equal to 1/2 times 1/2. That means 2 to the negative 3 has to be the same thing as 2 to the negative 3 is equal to 1/2 times 1/2 times 1/2 times 1/2. And that also means that 2 to the negative 4 must be equal to 1/2 times 1/2 times 1/2 times 1/2. So what we see here is that there's definitely a relationship between negative exponents and what's being repeatedly multiplied and how many times. So let's start by thinking about this example here, where we have x to the negative third power. What do we think will be repeatedly multiplied in this case? Jacob, what do you think?
X.
So we would think it would be x, but as we see up here, in our examples over here, when we have 2 to the negative third power, did we repeatedly multiply 2? No, we repeatedly multiplied 1/2, which is its reciprocal. So coming back over here to our example, if I have x to the negative third power, that negative exponent seems to tell me that I need to repeatedly multiply its reciprocal. What's the reciprocal of x? Adrian?
1 over x.
1 over x. So a negative exponent, and this is going to be part of our addition, or our definition, our negative exponent tells us negative exponents mean to repeatedly multiply the reciprocal. Okay, so a negative exponent means that we're supposed to repeatedly multiply the reciprocal. Jaquan. Coming up here, we know that the negative exponent tells us that we're supposed to be multiplying with the reciprocal. The 3 part of the negative 3 tells me how many times. So this is still, that doesn't change. This is still going to be 1 over x, since we're using the reciprocal, 3 times. And if we think about simplifying that a little bit further, we can think about that as the top times the top times the top, which is 1 times 1 times 1, over the bottom, which would be x times x times x, which we could actually rewrite as 1 over x to the third. So another way we can actually think about working with negative exponents is that all that really happened here is that we took this negative exponent and we moved it over to the other side of the fraction bar and made it positive. So that's another way we can talk about defining how we work with negative exponents. So we're actually going to have 2 definitions here. One definition is that negative exponents mean to multiply by the reciprocal. Another definition we can say is negative exponents can be flipped over the fraction bar to be positive. So using that second definition, I can immediately rewrite 4 to the negative 2 by flipping it over the fraction bar, by moving it to the bottom and making it positive. It's kind of a shortcut. But we have to know where that shortcut comes from. We're going to find that using expanded form is going to be 80% of the justification that we use in this unit. Your true understanding will probably come from using a lot of expanded form. So, this is a 4 to the negative second power. If we think about our first definition, that means I'm repeatedly multiplying what? What am I going to be repeatedly multiplying since I see this is a negative exponent? I should be repeatedly multiplying its reciprocal, which the reciprocal of 4 is 1/4. So the reciprocal of 4 over 1 is 1 over 4, and the exponent tells me how many times should I repeatedly multiply? 2 times. So it's 1 over 4 times 1 over 4, which is the same thing as 1 over 4 times 4, which this one is really easy to multiply out. If we wanted to find the actual value, it would be 1 over 4 times 4 is 16. So as you can see, there's a lot of different ways that we can write this particular value We can write it with negative exponents. We can write it in expanded form. We can kind of collapse that expanded form. We can write it in this simplified form with a positive exponent, or we can multiply everything out, top and bottom. So there's lots of different ways that we can represent this exponent. Jaquan. So for this, you should have written 2 times 2 times 2. And there is no simplified form, okay? Because there's no way to write this with an exponent that's any different than the way it's already written. So we're going to skip past the simplified form, but we are going to write its value. 2 times 2 times 2 is 8. All right, the next one I want to look at, I'm going to skip over one, and I'm going to come to this negative 2 to the positive 4 power. This is where that question that Jaquan had is really, really important. Kip yes or Kip no? Should I use the reciprocal? So you should be showing me a no. The reason you're showing me a no is because the exponent is positive. Okay? The base has no bearing on whether you use the reciprocal. Okay? So all this really means is what we're repeatedly multiplying is a negative number. Negative 2 times negative 2 times negative 2 times negative 2. We do have to be careful, though, when we're finding the actual value, because when we're finding the actual value, we have to think about good dates and bad dates. So there's a bunch of different ways you can go about doing this. Most of you will choose to use the associative property and say, well, negative 2 times negative 2 is 4. And negative 2 times negative 2 is 4. So 4 times 4 is going to give me 16. Positive 16. Okay? You have to be very careful with those good dates and bad dates. Yes, Jaquan? So we're going to skip down to these last two on the bottom. 3 to the negative 3rd power. Kip yes or Kip no? Should I be using the reciprocal? Yes, Katarin, why am I using the reciprocal? Yeah, the exponent is negative, all right? So we're going to use the reciprocal, which is 1 over 3. And we're going to multiply it 3 times. And we can write this in a simplified form. Because what we can see is that on the top, we would get 1 times 1 times 1, which is 1. And on the bottom, we have 3 times 3 times 3, which we could rewrite as 3 to the 3rd power. Remember, the other way we can think about that is we can actually take that exponent and flip it over the fraction bar to make it positive. It gives us the same idea. If we actually went through and multiplied it all out, we end up with 3 times 3 times 3 on the bottom. 3 times 3 times 3 is 27. So this would be 1 over 27. And the last one. Kip yes or Kip no? Should we be using the reciprocal? And Jasmine, why are we using the reciprocal? Because the exponent is negative. Now, this is where we have to be a little bit careful. What is the reciprocal of negative 2? Crescent, what is the reciprocal of negative 2? Close. There's one thing that you're missing there. The negative. We can't lose the negative in the process. So this is 1 over negative 2. And the exponent tells us to do this 4 times. 1 over negative 2 times 1 over negative 2 times 1 over negative 2. And if we multiply all the tops together, we're going to get 1. We can simplify the bottom because as we start to multiply the bottom, we're going to be multiplying negative 2 times itself. How many times? 4 times. So this is a different way we could rewrite this. Or we can actually do all the multiplication on the bottom. Negative 2 times negative 2 times negative 2 times negative 2. Well, I'm going to have to think about that. So on the bottom, it would be this negative 2 times this negative 2, which would be 4. And this negative 2 times this negative 2, which would be 4. Which means it would be 1 over positive 16. Okay? Are there any questions?